Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. And in this video lesson, we're going to wrap up our study of cooling towers. So the last thing that we wanted to talk about is the height of a transfer unit. So one of the ways we can look at this formula for Z is breaking it up into a height of a transfer unit times a number of transfer units. And the height portion is G, the gas flow rate, over the molecular weight of the air, K sub G times the interfacial area times P. But really, so the complication here is what the heck is KGA? And we can go back to chapter 7 and do it that way, but there are some other techniques. So one technique is this nomograph. Now a nomograph is sort of an old-fashioned graphical representation of a lot of experimental data in a fairly compact way. So if we look at this, what we have is we have cooling range is the scale down here. We have the water temperature, the cold water temperature, so the water exit down here. We have our L over G ratio, we have the wet bulb temperature of the air, and then we have also our Kg times V over L. So let's just look at that briefly. So let's consider this example problem here where I've got the cooling range is 10 degrees Fahrenheit, the water temperature is 80 degrees Fahrenheit, and the wet bulb temperature is 60 degrees Fahrenheit. And so I can plot these on this graph here. So 10 degrees Fahrenheit is down here, and so therefore it is the points along this line drawn in red. T sub L is 80 degrees Fahrenheit. It is this. This is sadly not quite a straight line. It's a bit of a curve. But so this point right here is a fixed point. And then if I want to also use a wet bulb temperature of 60 degrees Fahrenheit, then this is my second point. And I can now connect these two and read from this scale, Kg V over L, and up here the L over G ratio. And so reading this, L over G is approximately 2.25, very approximately. Kg V over L is approximately 0.77. And so it's a quick way of getting these answers. Let's look at this other case here. So in this case, we want to consider a cooling tower that's designed for cooling water that's available at 70 degrees Fahrenheit on a day when the wet bulb temperature is 40. And the approach, the cooling range is 15 degrees, and we want to estimate KVL and L over G. So here's another one. So take a moment, pause the video, and make sure you can do this. And then I'll come back and work it. Okay, so I've started by drawing in given information with a wet bulb temperature of 40. And I don't think I did a great job of drawing that line, but the KVL or KV over L is approximately equal to 0.56, and L over G is approximately equal to 0.35. One final thing that I want to mention is dehumidification. It isn't such a common need as a cooling tower. This basically is the absorber version of a cooling tower. So the operating line ends up above the equilibrium curve, but all of the steps are the same. All of the formulas really are the same, but it's going to be above the equilibrium curve. And that's all I'm going to say about that because it is sort of an unusual situation. So this concludes our study of cooling towers and absorbers and strippers. We will be taking a test on that soon, and we'll review for that in class on Monday. Thank you very much for your time.